in class, we've used some terms with relation to electricity that I want to make sure everyone's okay with. Specifically voltage and current. I'm also going to talk about resistance a little bit, but we don't use that term as much in the particular area of the lab we're in, although it's still a relevant thing. So, when we talk about voltage, the context we've been using that in for class lately has been we've been talking about voltage differences in a reaction. So for example, if we look at a half cell potential for, let's say, Ag plus an electron is in equilibrium with silver solid. And if you look up the E naught cell for that, you get that that's plus 0.799 volts. So I think a question that might be reasonable to ask is, okay, so what does it mean that 0.799 volts? What is that voltage about? So voltage is a measurement of potential difference. And so what we mean by that is that it's related to basically how much push there is to get the electron to go from one place to another. In this case, going from being on silver solid, whether it would stay on silver or if it's going to get released onto silver plus. So if you've got electron floating, how easy is that to make that happen? A good way to think about voltage is with a water pipe analogy. So think of how pipes work. So voltage is kind of like water pressure, right? So if you've got lots of pressure, it's going to push more water through your pipe. And so voltage is that pressure that you're pushing with, in a sense. So with a chemical potential, that's that push that's happening there. Now, by itself, water pressure doesn't lead to a large amount of water going through. So it'll be based on the design of your pipe that you're working with. So, for example, if you had a really tiny pipe versus a really big one, it's going to make changes into how much water is actually going to go through. Those changes in like the structure of your pipe, or maybe you've got something stuck in it or something, those are related to resistance. So resistance is going to be something that changes those properties of how much water pressure you're going to need to get through a certain amount of water. Now, the amount of water that actually travels through, that's our current in our case of electricity. So current, in our case, rather than being water flowing, it's electrons flowing. So current, measured in amps, is related to how many coulombs of electrons are traveling across something. So in our reaction, the amount of electrons moving is going to be our current, and then voltage is related to how much push there is to get that to happen. And so as that push goes down, you're going to get less and less of that happening until eventually, if we get to 0 volts, we're now in an equilibrium state. And so in an equilibrium state, we've got as much forward as we do backwards in our chemical reaction. So if you get to 0 volts, it's going to happen where you get just as much silver solid as silver plus, because they're going to go back and forth. When you form additional silver solid, you'll form just that much silver plus back. It's not that they're the same amounts, because they're going to be different values and different concentrations, but that as quickly as you're making new silver solid, you're making new silver plus from that silver solid, since the reaction can go both ways. So in that sense, voltage is a way of knowing which way the direction the reaction is going to go under current conditions. As a reminder, E naught cell is specifically standard state. That means I have 1 molar silver plus if I'm talking about a standard state cell. So if our voltage is positive, then we've got a spontaneous reaction. So if we set something up so this half reaction can happen, so that electron has to have somewhere to go, right? To come from. So we've got some other half reaction that's providing the electrons. As long as that's the case, this reaction, if it were compared to something of a voltage of 0, should go forward. Now, when we talk about voltages, those are always relative to each other. So while we say this is 0.799 volts, that's in relation specifically to the standard hydrogen electrode. So what I mean by that is if you compare this to the reaction, losing my pen, there it is, 2 H plus 2 electrons is in equilibrium with H2 gas. This reaction, when it's standard state, which would mean 1 molar H plus, 1 atmosphere of pressure H2 gas, would be an E naught cell of exactly 0 volts. So we've defined it that way, that this is our standard, and so everything we're using is comparing to this standard. So if I were to set up a cell where I was taking hydrogen gas and forming 2H plus off of it, and that's how I was getting my electrons, and I connected to a silver containing cell in a way that they would be able to, electrons could flow, I could get the silver to react compared to the hydrogen. That I could spontaneously take Ag plus, turn it into Ag solid, and I could take H2 gas and turn it into H plus. That could be the exchange of reactions I have. And if I go and balance that, I would get something like H2 gas plus 2 silver plus because the top reaction only has 1 electron and the hydrogen has 2, so I need twice. The top reaction to happen 2 times would be an equilibrium with Ag solid plus 2H plus. So let's say I did that. Let's say I tried that setup. Well, as written, this is good to go. Yes, so that would be, I was making sure I didn't do it backwards. I'm still bad about that because I still find these hard. I still find these, I have to think about them through really well. So yes, this would still work out. Our cathode minus our anode. Our reduction is happening of the silver plus. Hydrogen is what's being oxidized. So as a reminder, our E naught cell will be, if we look up reduction potentials, which is what you're going to have provided to you, that would be that we would take E naught of the cathode, aka where the reduction happens. We would subtract E naught of the anode, where the oxidation happens. In this case, the anode is our standard, so it's 0 volts. So it'd be 0.799 minus 0, so we'd have a 0.799 volt cell. Now, because that voltage is positive, we would have a spontaneous reaction. So if I left that cell for a time and I didn't try to adjust the concentrations of anything, over time, my silver plus would get used up and my hydrogen gas would get used up and I would form more H plus. So I would make my system more acidic, but I would have less silver plus and less H2 gas. As those adjust, eventually I get to a concentration where I get to equilibrium. So let's look at that idea next now. So we can actually calculate an equilibrium constant from using a cell. So at equilibrium, that means that we have no net change in electron flow because the forward and backwards reactions exactly match in terms of we make one thing as fast as we get rid of it. So we have, as a reminder from earlier in class, you have the Nernst equation can be solved for each half reaction, and we can set that equal to each other side to solve for the equilibrium constant. So what this leads to is a relationship that is, there's a proof of it in your text for, and in this text it's the SCOOG analytical text on page 484, 485, but it proves this statement that if you set those two equal to each other and you solve for it and you convert it from natural log to log, you'll get this equation here, that the log of KEQ, the equilibrium constant, is equal to the number of moles of electrons involved in the reaction times E naught cell divided by 0.0592. This happens to do with solving, you've got two Nernst equations, one for each half reaction, and there's a proof in the text that goes through and does that. So I'm going to look at this reaction down here, Fe3 plus I minus goes to Fe2 plus I3 minus, and I'm going to solve for this equilibrium constant. So let's take a look at how that would go. So we've got to split this up into half reactions. So the first one, I'm going to do it up top here because this one's fairly straightforward, right? Fe3 plus being at equilibrium with Fe2 plus. The only difference there is a difference of 1 electron. So we're adding an electron on the left. Adding it to Fe3 plus, it becomes Fe2 plus. Now let's look at the other reaction. So we have I minus in equilibrium with I3 minus. Now first we have to balance the atoms. We need 3 of these on the left to make I3 minus on the right. And so now our oxidation states are different in the sense that this I3 minus overall is a -1, which means it'd be like having 1 iodine be -1 and 2 of them be 0. On the left side though, all 3 are -1. So you have -3 on the left, -1 on the right. So that means we're losing 2 electrons in this process, so they're a product. So we have 3I minus is an equilibrium with I3 minus plus 2 electrons. Now, from there, if I want to add these two reactions together, this means the iron, I would need to double all of these so that the electron numbers were the same, and then when I add them together, I get a balanced reaction that says that 3I minus plus 2 Fe3 plus is an equilibrium with, and let me see, well, my head's not in the way yet. That's good. So, and then on the product side, we have I3 minus plus 2 Fe2 plus. So now we have this reaction, and now you can find the voltage difference for this, because I'm going to need that, my E right minus E left. If I look these up, E right, so I've got a table in front of me, so that's going to be, by right, we mean our cathode. And so our cathode is the iron, because that's the one gaining electrons, so it's being reduced. I still have to go through that every time. So this will be 0.771 volts. Then E left, if we look it up for I3 minus, is going to be 0.615 volts. Now, when you look in your table, you're looking at a reduction potential. And so this minus sign here, that's what's taking into account the fact that you're not using this as a reduction in this case. You're using the oxidation form of the reaction. So you do not need to change the sign as well with this value that I looked up. So the table says 0.615 volts. That minus takes care of that. If you change it to negative 0.615 because you're looking at the oxidation and you subtract it, you've effectively not effectively, you have. You've tried to account for the difference of the reaction 2 different times and you've accidentally made a mistake. So make sure you get the reduction potential and plug it in there if you're using this equation. And the number of moles of electrons is 2 because we have 2 electrons involved there. And so, let me see, 0.771 minus 0.615 times 2 divided by 0.0592. And so then we get that the log of KEQ is equal to 5.27. I then need to undo the logarithm, and it's base 10, so 10 to the power of each of these gives me an equilibrium constant equal to, let's see, 1.86 times 10 to the 5th power. Is that right? Yep. Okay. I was making sure I had my values right for some things. Yes. Okay. So that is my equilibrium constant now. So I also did a proof of this when we were in our problem session as well last week. But if you weren't there or don't remember it, you can check the textbook for an example with that. Okay. Now I've got 2 other problems I want to solve for things we did in class. So we're going to do some practice calculations. First, I'm going to take a reaction, I'm going to balance it, and then calculate its standard cell potential. So when we're doing this, so let's break this up. So first I'll do the chlorine minus part. We can do that first. So Cl minus, aqueous, is in equilibrium with chlorine 2. Chlorine gas, there's 2 of them, it's diatomic. So I need 2 chlorine ions to make this balanced. Now when I go to balance the electrons, since there's no oxygens or anything to deal with, I have a -1 oxidation state on the left side and a 0 oxidation state on the right side, since chlorine's on its own, connected to itself, not charged. So I'm going from -1 to 0. Each time that happens, that's going to release an electron, and I'm doing it twice since I have 2 chloride ions, and both are losing 1 electron to form Cl2 gas, so this is going to be +2 electrons. Then, for my other reaction, I've got Cr2O7 2- aqueous plus chloride aqueous is in equilibrium with chromium 3+ aqueous plus chlorine gas. Note, in some text you'll see, and I just realized I did this shorthand, we will end up not writing aqueous on the ions. We'll assume, hey, we're doing this in aqueous solution, it's got to be aqueous, and then we'll just put the phases on the other stuff, like the gases, liquids, and solids. So that's why that happened there. Oh, why did I just rewrite the whole thing? I did not mean to rewrite the whole thing. That was not useful. Let's just talk about the half reaction part. So Cr2O7 2- at equilibrium with Cr3+. There we go. That's more useful. So I need to balance my chromium first. So I'm going to need 2 of these. Then I'm going to deal with the oxygen. There's 7 oxygens on the left, and since we're happening in water, we can add water molecules. We're going to add 7 of them. And since I have 7 water molecules, I've now added some hydrogens. We're told this is in acidic conditions, so therefore you're going to have a bunch of H+ around, so I should add enough H+ to balance those. So that'll be 14 H+, and it's H+ aqueous. And so now we've balanced all the atoms. We got to figure out the electrons. On the right side, chromium's 3+, it's on its own. Here, oxygen is -2. There's 7 of them, that's -14. I want to get to the overall charge is -2, so I want my oxidation state to be -2 overall. So I'm at -14, I need the chromium to be +12, since 12 minus 14 equals -2. If I want chromium to overall be +12, one of them has to be +6, since there's 2 of them. So we are going from +6 on the left to +3 on the right. That means that we are having to gain 3 electrons for each chromium for this to happen, and we're doing that twice. So this takes 6 electrons to make this exchange work. So now, we can now figure out if we add these together. In total, when we combine them, the electron, we've got to take the top one and get 6 electrons. So that's going to multiply everything by 3. So you'll have 6 chlorides, 3 Cl2s, 6 electrons. We go to add them, the electrons cancel. So we'll have 6 Cl- plus 14 H+ plus Cr2O7 2- is in equilibrium with 3 Cl2 gas plus 2 Cr3+ plus 7 waters. And so now we have a balanced chemical equation. The last question asked us, part of the question is to calculate the standard cell potential. So I need to look up what all these standard cell potentials are. I'll also note that the top equation with the chloride, that's where I'm losing my electrons, so that's the oxidation, whereas the bottom one, that was a reduction, since the electrons are on the reactant side. And so when I go to look up their reduction potentials, I get that this one for chloride minus is... I do not have it on my sheet. Just a second. I do have my chromium, though. So chromium is 1.33 volts. I left my textbook at school today, so I'm going to very quickly, on another slide, Google real quick, what is my voltage potential difference for Cl minus to Cl2? Note, I might get a slightly different number because you'll see these in different values, depending on what you're doing. So some texts will have slightly different values. So if you're working through this and you use the textbook from school has a slightly different value, don't stress. So this is negative 1.36 volts, right? Yeah, Cl minus to Cl2, okay? So what that means is now, if I want my E0 cell, we have the reduction is our 1.33 volts minus a negative 1.36 volts for our chloride change. And so as written, this is definitely spontaneous. We have 1.33 plus 1.36 because the two negatives become a positive. And so we have 2.69 volts as our E0 cell. So this is the standard potential for this particular reaction as written, and it's how you balance the reaction. So hopefully that helped out some. We got one more problem to do, so I'm going to erase erase all ink. Bring my pen back up and let's do one more. So I'm going to look at the theoretical cell potential for the following cell. So as a reminder, we've got this represents our salt bridge, so we're going to split this up into two parts. The left side is going to be our anode. That's where our oxidation happens. The right side is going to be our cathode. That's where the reduction happens. So we need to write our equations as oxidation and reduction. Also, there's this platinum at the end. Because Fe2 plus and Fe3 plus are both aqueous ions, they need a surface to happen on for the electrons to flow into our cell. So that's why the platinum's written there. It's not going to participate in the reaction. It's just really good at, we can easily dump current onto it or have electrons flow into it and flow into the reaction. Also, I've noticed this pattern, and I will fully admit I don't know the exact ordering we always use. I have checked that this is the order that a lot of cells will be written in, Fe2 plus, Fe3 plus. The important part is the right side is the cathode, but you do need to set it up as a reduction reaction. That it's not always going to be written actually from left to right in terms of the electrons flowing always from the left one to the right one. It's just the overall left side is the anode, the overall right side is the cathode, but you have to figure out which direction that would happen in. So you will sometimes see them written in a particular order. That doesn't mean that Fe2 plus is on the left and Fe3 plus is on the right. I don't actually have a good answer for that one yet. I'm sure there's a good reason, and I will figure it out and tell you in class in the future. But so the left side is anode, right side is cathode. So if it's anode, that means we want to be losing the electrons. So zinc is, we're going to have zinc on the left, and it would be in equilibrium with zinc 2 plus on the right. Since they have different oxidation states, and this goes from 0 to 2 plus, that means we would be losing 2 electrons. Now with Fe2 plus and 3 plus, we want to set it up as a reduction. To do that, we actually need Fe3 plus on the left, since that would be the species that would be able to gain an electron. So this is Fe3 plus. I'm going to mute myself. I'll pause. I'm going to sneeze. Okay, I could have just not told you I was pausing, but it's fine. So Fe3 plus is in equilibrium with Fe2 plus, and so that'll gain an electron there. And now if we want to combine these two, we need to have a 2-electron exchange, which means we're going to double everything in the iron case. So we go to add these up. We get zinc solid plus 2 Fe3 plus is in equilibrium with zinc 2 plus 2 Fe2 plus. Now we're asked for the potential here. And so we have to first find E0 cell for the standard state and then adjust it using the Nernst equation. So our E0 cell, we need to know what both these are. So I need to get that pulled up. Let's see. So for zinc, for our zinc, if I look up my E0 cell, I get negative 0.763 volts. If I look up my iron 2 plus and 3 plus, I get, where are you? There. 0.771 volts. And so if I go to E0 cell, cathode minus anode, I would get negative make sure I got that right. I have these written reasonably? Yes. So negative 0.763 volts minus, oh wait, just kidding. I knew something felt off. So I wrote anode and cathode up the top here, and I let myself get confused that cathode is attached to this. No, we're doing, in the zinc case, this is where our oxidation is happening. So that's going to be our anode. And then the iron is where our reduction's happening, so that's our cathode. So, see, I knew what I thought my answer was, and that didn't feel right. So we have 0.771 volts. And then we have, okay? So that's going to be for the cathode. And then for the anode, we have minus a negative 0.763 volts. So we have an E0 cell equal to, let's combine these two, 1.534 volts. Now I have E0 cell, and so now we need to adjust it using the Nernst equation. So we're going to have 1.534 minus 0.0, oh, I got to remember, it's 0.0592. I'm fair. Make sure I got that right. Nernst. I'm going to back up for a second. Yep. Sorry about that. So I had to make sure it was 0.0592 divided by n. In this case, n is 2 electrons. And then we have the log of the equilibrium constant. So that's products over reactants. So in our balanced equation, that would be Fe2 plus squared, zinc 2 plus, divided by Fe3 plus squared. So we're going to plug those values in. Fe3 plus, we said, was 0.1000. This zinc 2 plus here is going to be 0.0240. This Fe2 plus is going to be 0.0340. I really could have given myself more space. But 0.0340 squared times 0.0240 divided by 0.1 squared. Take the log of that, and then multiply it by 0.0592 and divide by 2, and then 1.534 minus that. And so I got a small change, which is now our E is equal to 1.610 volts. And so that will be our potential at these concentrations. So it changed it a little bit. It's now slightly more spontaneous, as written, rather than less. So that gives us our potential. And so that's how we take that notation, turn it into balanced chemical equation, and then use those particular concentrations to figure out what the new voltage would be based on the Nernst equation. So hopefully all those three things weren't too hard, or the couple things we did. This is the stuff we worked on in class for people that missed class, that weren't available to be in class today. Also, in general, just if you find this in some future date, hopefully it helps you out. So I will see you in class on Wednesday, or if you're at a different time seeing this, I hope this was helpful. And if you know me, maybe I'll see you. And if not, you can see me on YouTube.